Well, good afternoon. Sorry. This is Charles Fowler. This is Fiscal Science 112, our first Zoom meeting with this. I hope it's working. I see that I'm in it. I hope that some of you will be able to log in and join the meeting. Where we left off last time is we're in chapter 2, which is motion, and we're in section 2.2, I believe it is, which is measuring motion. And we had talked about uniform acceleration last time. I'm sorry, I wish I could get this out of the way, but I can't find any place to put it. Maybe it'll be less in the way if I put it down here. Let me try that. In my last class it was better at the top. Maybe this will be better down here. And again, just a review, uniform acceleration is also sometimes, it's occasionally called constant acceleration. The only little deal with constant is it has to be straight line acceleration, which of course would be constant if you're thinking of acceleration in terms of vectors. But anyway, when you do have uniform acceleration, straight line, constant acceleration, another way to calculate average velocity is simply the sum of the initial and the average of the initial and final velocities, which leads to this formula here. And this is on your page 31, I think. 2-7 is the other number that's given here, and this is equation 2.3. Average velocity is equal to final velocity plus initial velocity over 2, divided by 2. Now, if you recall, we had an earlier definition for average velocity, which is I was trying to think what letter they used in here. I want to use some books use S, some people use D. I'm trying to think which this one used. I'm teaching, yeah, they use D. Average velocity is d final minus d initial divided by time. Distance divided by time. I was calling this delta d, or the book just calls it d over t. Okay, any one of those will work. And in the lab that we were going to, oh, Gunnar, are you here? Can you hear me, Gunnar? Wait, I may have forgotten to do something. Hold on just a minute here. Nope, that's not what I wanted to do. I'm going to have to come back to this in a minute. I forgot something. Hold on. Yuck. I forgot to share my screen. Sorry about that. Let's go back to this. Okay. Okay. Yeah, I should be sharing now. Gunnar, are you still there? Did I lose you? I'm awfully sorry. Okay. Oh, you're there. Gunnar, are you there?
Yes, sir, I am.
Oh, good deal. Welcome. You're the first one in the class that I've been able to tell so far. Okay. Can you see the screen?
Yes, sir, I can.
All right, good. I had forgotten to open the screen. I did that last time too. And the first person that came on the last class couldn't see it, and I realized that. I'm sort of starting over here. Are you okay to run the 2.5 hours here? Or you're not at work or anything, are you? I can't hear you.
No, I'm sitting on my couch right now.
Oh, okay. Well, I had one Friday, I believe it was. Okay. What I had mentioned before, and if you go back and see the YouTube video, you'll see I do this twice, since you just came on. Remember earlier we had average velocity was just distance over time. That's how the book talked about it. I called it d final minus d initial. In other words, your displacement over your time interval, change of time. All those mean the same thing. And in the lab we would have been having today, had we been meeting today, we would be using both of these formulas, and that way coming up with a way to calculate your final velocity. There are some virtual labs out there. I don't have access to them right now. I'm going to try to get them through my physics instructor, and I know he uses them all the time, so I'm going to see if I can find those. But we're not going to have a lab today. So we'll be ending at 3:45, and it'll just be class today. And hopefully by next time, I'll have some virtual labs out there. They're going to be awfully easy and not going to be nearly as involved as what we would be doing in class. But it's all I can do. I can't think of any other way to do the lab. So, you okay with that? I don't know if you're still there or not. All right, let me move on. Example 2.5 is near the bottom of, at least in my book, it's page 31, and yours it may be 2-7, whichever it is, or maybe you have both of those numbers there. Let's do example 2.5. And let me clear the writing here, and we will do example 2.5. An automobile moving at 25.0 meters per second. So that is a velocity, obviously, and that's your initial velocity, 25.0 meters per second. Comes to a stop. What that means is your final velocity is then 0 because it came to a stop, no longer moving, okay? And it happened in 10 seconds. Well, that would be your time interval. What I call delta t, the book usually just calls t, okay? I'm sorry, it's 10.0 seconds, okay? 3 significant digits. Well, comes to stop in 10 seconds when the driver slams on the brakes. How far did the car travel while stopping? So the question here is your d, the distance. That's what we don't know. How far did the car move while it was trying to stop? Okay? Now, if you recall, we had an equation for d. I had it up on the board just before I erased these, and it was, if you recall, d over s is equal to v, average velocity. Okay? Now, here's an assumption we're making here. The automobile moving at 25 meters per second comes to a stop in 10 seconds when the driver slams on brakes. Now that when the driver slams on brake, here's our assumption, that he is now undergoing uniform, constant, straight line acceleration, or in this case, deceleration. He's slowing down at an even, regular pattern. So with that in mind, we have another formula for V bar, the one that was just up here. In fact, I'll show it again, right there. V bar is V final plus V initial over 2. Where your V final, V bar, V final plus V initial over 2, the average between the first two. This is true anytime that uniform, constant, straight line acceleration. Okay? That will be V final was 0 plus V initial is 25.0 meters per second divided by 2, which is 25 divided by 2 is 12.5 meters, and this is meters per second. That's your average velocity. The 2 has no units with it. That's just a half. You're dividing by 2. Okay. Now that we have that, that's our V bar. We're looking for D. If D over S is equal, D over T. Goodness gracious, you let me get away with that. You should have corrected. Okay. D over T, or delta T, whichever you want to use, is equal to V bar. Well, then multiply both sides of this by T. Your T's go out, and you have D is equal to V bar over T. Well, here's your V bar. That's 12.5 meters per second. Multiply that by your 10.0 seconds. The seconds cancel out, and that gives you 125 meters. Whoa, okay? The guy was traveling at 25 meters per second. Now, I don't know exactly how far that is. I mean, how fast that is in U.S. customary units. I think it's around 60 miles an hour, somewhere in that ballpark. Okay, so at 60 miles per hour, slamming on brakes, takes him 10 seconds to stop. How far did he go in those 10 seconds? 125 meters. Now, what's that? That would be the entire length of a football field, counting, pretty close to counting both end zones. Okay, maybe even a little longer than that would be how far it took him to stop if he was. When he slammed on brakes, it took 10 seconds to go from 25 meters per second to 0. That's why you don't tailgate, folks, because there's no way if a truck were to jackknife ahead of you and you don't have a chance to, you don't have a football field length or so to stop, you're going to hit him. Okay. Let's see if that's what the book got. Sure enough, 125 meters. Now, there's also a 2.6 here. Okay, and let's not change anything here because 2.6 depends on what it is. What was the deceleration of the automobile in example 2.5? Well, we have V final, we have V initial, V final, and we took the time interval. That's your acceleration. A is equal to V final minus V initial divided by T. Okay? Just like average velocity was the change of distance over change of time, average acceleration is the change of velocity over change of time. Very similar formulas. And what we have here, our V final was 0 minus our 25.0 meters per second divided by our 10.0 seconds. Okay? Not a very hard calculation to make here either. Negative 2.5, because you're dividing by 10, move the decimal one place over, 2.50 meters per second, which we usually write meters per second squared. Changing speed at 2.5 meters per second each second, or an acceleration 2.5 meters per second squared. And they put the minus sign in front too. That indicates it's a deceleration rather than an acceleration. All right. There is a concept supplied here in the middle of page 32. It might be listed as your page 2.8. acceleration patterns, and it says suppose the radiator in your car has a leak and drops of fluid fall constantly once every second. It would be pretty regular to do that. What pattern will the drops make if you're accelerating your car at a stoplight, or when you drive at a constant speed, or if the car comes to a stop? Then it goes on about that. There's actually a better illustration of this that I've seen or read or heard about in another physics book sometime or another. If you had an empty parking lot and you could do this, have one person sitting by an open door in a car, and he has a series of the traffic cones, little traffic cones he could put out, rear seat, opening probably on the right-hand side, it doesn't matter. And as the car is doing these three things, accelerating from stop to a certain speed, every second he puts out a cone, okay? Just puts it on the pavement. And then have the car slow down and stop. Every second put out a cone. Watch the pattern of those, and then drive across the parking lot at a constant speed, put out a cone every second. You would see that when you're speeding up, the cones get further apart. When you're slowing down, the cones get closer together. And when you're traveling at a constant speed, the cones are equidistant apart. It's a pretty interesting thing. If you and a buddy want to do it sometime, that is doable. Okay? Just need a good stopwatch type thing on your clock. Okay. Let's move on to forces. This is bottom of page 32, left-hand column. Okay, a little bit of historical background here. First, and we referred to before the ancient Greeks, Aristotle being the primary one among them. They were many times much more philosophers than they were scientists. But Aristotle was probably the leading, what they called, natural philosopher, looking at nature and putting together ideas and concepts about it. I don't know if he had a concept of force, okay? Here's one of the things he claimed, though: heavier objects fall faster than lighter objects. Now, that sounds like it makes sense. From one viewpoint, it kind of makes perfect sense. It just seems like that would be the case. Okay. However, another is that objects moving horizontally require continuously applied force. So here he is talking about forces to keep moving in that direction. Okay. Do I have somebody else here? Is that Chad? I can't tell for sure.
Yeah, that's Chad.
Oh, good. Welcome to the class. Okay. Now, as y'all fill up the page, I don't know if we'll be able to see the PowerPoints or not, but they're all going to be out there. I don't think this would be projected. They'll be out there on the YouTube videos later. So anyway, welcome to the class. Having any trouble getting in or locating it? Did you have any trouble getting to it or locating it? The Zoom? No? Okay. I saw your lips move, but I can't hear very well, so, okay. All right. Are you at work?
He is actually at work.
Huh?
He is at work.
Oh, I see. Okay. Well, hang in what you can. It'll all be on Blackboard and YouTube videos later. Okay. So anyway, he also claimed that objects moving horizontally require constant, continuously applied force. Okay? And he did this basically thinking about it and, some observing of nature. Sure enough, if you roll a ball across the floor, ultimately it's going to stop if it doesn't hit something. So yeah, it does you would think it needs a force to keep it running, rolling. However, here came Galileo, then followed by Newton, and they were like, I think the year Newton was born was the year Galileo died. I mean, it's sort of like they tag teamed with each other on the way in and out. But anyway, they showed that all objects fall at the same rate. Now, it may not seem like it makes sense, but it truly does. And we'll see why in a bit. No force is required for uniform horizontal motion as long as you don't have any opposing forces. Okay? And then finally, they did their reasoning based on measurements and experiments, not what Aristotle did. He just thought about it and said, yeah, this seems reasonable. And of course, for about 2 or 3, I don't know how many centuries, everybody, if Aristotle said it, they believed it. And that was it. Okay? So, what is a force? In your text on page 32 or 2-8, whichever page you have, on the right-hand column, a force is a push or a pull. Okay? Simple definition, a push or a pull capable of changing an object's motion. Okay? The overall effect is determined by the vector sum of all the forces, and that's often called the net force. Okay? I think I'll move these blocks to the top now because they're getting in the way of reading. Okay. Well, let me see if I can move them over here, if that's any. I'll do it there. Okay. The net force on an object. Here's the example, a ship in the water, okay, a cargo ship of some nature. And here's Tiffany. Are you in with us, Tiffany? Yes. All right, good to have you. Did you have any trouble getting in?
A little.
I'm sorry? Okay, I can't hear you very well, so let me get your present here. Today's the 17th, and Thursday will be the 19th. All right, we have Gunnar here. Heath, I couldn't remember your last name. And we had Chad White, for a little bit anyway. And then we had Tiffany, have Tiffany now. Good deal. Now, I was telling Gunnar, and I don't guess I said it when Chad was still on, I don't think we're going to be able to manage a lab today. I'm going to have to see if I can find some virtual labs, and I just did not have time yesterday to locate those. I thought Dr. Bryant was going to be on campus yesterday. I was going to get them from him, but he must have been practicing social distancing because he didn't show up. So anyway, I'll have to deal with this probably when we're in our lab period, which we won't be having today. I'll be looking and seeing if I can come up with some. Okay, it seems like maybe 2 more have joined the class. I don't know for sure, but yeah, Josh Mathewson, right? Your name showed up anyway, so I assume you're here. But anyway, we're talking about forces, push or pull. This is on page 32 of your text, or 2-8. And a push or a pull capable of changing an object's motion. So here we have a cargo ship of some nature, and it appears that you have a couple of medium-powered tugboats, 1,000 units each, pushing on the starboard quarter, okay, back there near the rear on the starboard side, right side of the ship. So if they're both pushing that way to the east, then the net force on the ship is 2,000 units to the east. That's just regular addition because they're in the same direction. So that's the vector sum if they're in the same direction. However, if they got their wires crossed and one's on the starboard side of the ship and one's on the port side, one's on the right, one's on the left, they don't know each other's there, and they're pushing against each other, the ship has no net force. lots of force on it, but no net force because the vector sum is 0. Okay, you do direction with units. Okay, however, if you had the big tugboat on the right-hand side, on the left-hand side, and the smaller tug on the on this side, and they're pushing, the smaller tug saying, what in the world is happening? The ship's coming over me when I'm pushing against it. Well, that's because the net force is 100 units to the west, 1,000 units to the west. That's how vector addition goes. And then when you have angles, it gets even hairier, okay? But in practical everyday situations, you run into net forces all the time. If I can get a, I'll use this one. For instance, when we moved into the house where we currently are living and where I'm speaking from today, we had a couple of really scrawny, crooked, ugly little pine trees, but tall pine trees in our side yard. They were growing underneath some monstrous oaks, so they weren't able to go straight. They weren't able to find much light, so they were weaving their way trying to find light under the canopies of those two trees, and they grew to be really spindly, ugly little trees. Well, my father-in-law and brother-in-law came down from Huntsville bringing a chainsaw. This is right when shortly after we had moved in. And what we did, we threw a rope as high as we could up the tree, and it came down the other side, and Dan got on this side, I got on this side. We pulled, the tree was here. Mr. Brazil was using his chainsaw at the base of the tree. He cut the tree. We were pulling to make sure it didn't fall into another tree, into the house, or anything else, and we were able to do. Now, we would have had the greatest net force if we had pulled this way, both pulling in the same direction. But that wouldn't have been smart because then the tree would have fallen on top of us. So what we did, we got at a little bit of an angle, so we had a majority of our force in this direction, okay? But Dan was pulling slightly this way. I had the majority of my force pulling this way, but had a slight deviation that way. So the vector sum of our forces was less because these two portions of the vector of this total force canceled each other out. This was to the left, that's to the right, this to the left. But the sum was the total of these two, and that pulled the tree down in the direction we wanted it to go without damaging any other trees or property or house or anything else. You do this all the time. If you happen to glance as you're driving along, my younger brother was worked for a small rural electric power company, and used to be called a EMC. There was another name for it. But anyway, it's hard to ride with him because he's always looking up at the power poles. And if you'll notice those power poles sometimes, especially on a curvy road, my wife's parents had a place up in Winston County, and none of the roads up there, they followed the ridges and stuff. So the power lines would be crisscrossing the road back and forth, and the poles would not be in a line. So therefore, the force of the wires would tend to pull the poles toward the road, which you didn't want. So they have guy wires in the back pulling them back in the other direction. Notice that sometime when you are on a curvy road and the power lines are not in a straight line, you'll see that they always have a guy wire from the top of the poles to somewhere down at the base, far from the base, but at the ground, far from the base, pulling the pole back in another direction. All vector quantities, okay? So, anyway, that's the difference in scalar addition and vector addition. And like we said here, when you're dealing with forces like displacement, like velocity, like acceleration, they are vector quantities. So the net force is not just the sum of forces, the vector sum of the forces. Okay. Now, they sort of throw this in, and it's rather a strange place to put it. There are really four fundamental forces, and these are the types of forces they call force at a distance. This is not like you pushing on a chair or pulling on a cart or something like that. Those are applied forces. These are the four fundamental forces of nature. The most basic of all interactions, one is gravitational force. These are mass interactions. The formula for this, which we'll hit later in the chapter, you'll see it's the product of the two masses involved. The mass of the bigger object and the smaller object, you multiply those two together. They're used for all sorts of things, not the least of which are motion of planets, stars, galaxies, These are all the result of gravitational forces. The next, and believe it or not, stronger force is electromagnetic force. Here you're having charge interactions, not mass interactions, charge interactions. Now, one thing about gravitational, all gravitational forces that we know of are attractive. There's no such thing as a repulsive gravitational force. You just can't have it. They're always pulling objects together. However, in electromagnetic forces, you have charge interactions and you have different rules, okay? For instance, in electric charges, like charges repel each other, unlike charges attract each other. You don't have that in gravitational forces. All of them are attractive forces. In magnetic forces, okay, like poles repel each other, unlike poles attract each other. Very similar to electric forces. You have both attractive and repulsive. Now, what difference does this make? This is what builds atoms and molecules. This is what chemistry is based on, the electromagnetic forces. Lots of other things that depend on that too. I mean, your starter engines and your starter motor in your car, your generator or your alternator. I mean, all these are electromagnetic in nature. And here we have Zane. Welcome, Zane. Are you at work too? Okay, connecting to audio. Glad you were able to make it. Okay. Are you able to hear? Can you hear? Can you hear me, Zane? Okay, great. And do you see the screen? Okay, super. Okay, welcome to the class. But all of chemistry, atoms, molecules, they all hang together because of electromagnetic forces, as well as many other things. Now, the next two forces are even stronger, even though number 3 is called a weak force. It is, okay, wait, let me back off to electromagnetic. Why do I say electromagnetic forces are stronger than gravitational forces? Well, picture this. What if you had little pieces of paper on a tabletop, okay? And say you comb your hair with you have hair, I don't, with a comb, a rubberized comb. And with that rubberized comb, now you've moved electrons off the hair onto the comb. You reach over there near the pieces of paper and you can sometimes lift them without touching them. They will come up and catch on the comb. Well, those paper are being held to the tabletop by the gravitational force of the Earth, but your electrostatic force pulls them up. So therefore, electrostatic forces are stronger than gravitational. I think we lost Zane, but I still see where he was sitting, but he's no longer sitting there. Now, the weak forces are certainly not weak. They are forces involved in certain nuclear reactions. And you talk about powerful forces, these have to be very powerful forces. And that's really all the book says about them. They don't give much more detail than that, and this course isn't prepared for that, okay? The strong nuclear forces, now this really illustrates why they're stronger than electromagnetic. If you think about what the nucleus of an atom is, Okay, a nucleus of an atom is a bunch of protons, okay, positive charges. I mean, they're packed in that nucleus, okay? Now, there's some neutrons in there too, usually more than there are protons, but still, they're neutral charges. There's nothing that's holding them there. The protons, however, by electrostatic forces, should be forcing each other apart. They should be pushing like crazy apart, and yet they're held together. What's holding them together? We don't know for sure. It's just strong, what they call the strong force. It has to be strong to keep a nucleus from exploding. So electrostatic and magnetic forces much weaker than strong forces. Okay. Those are the four fundamental forces. I guess since they were talking about forces, they thought they had to mention them. What we're going to be dealing with is, and we're going to a new topic now, this is 2.3, beginning on page 34 or 2-10 in your text, and that's horizontal motion on land. Now, this was to be the lab today, okay? I can't figure out any way to do the lab. I'm going to try to find some virtual labs and see if I can do those. They're going to be much easier, much shorter, unfortunately, than what we'd be doing if we actually had a chance to do lab together. But with this virus, we don't want to be together. Looks like Zane is in an ideal situation. Looks like you're out on a porch. Is that right?
Yeah, I'm up on the phone.
Yeah, so that's, you can't get much better than that. Okay. I was contemplating recording this from the backyard because it's so pretty outside today, but I was afraid our Wi-Fi wouldn't work as well out there. So here's horizontal motion on land. This is what some people call natural motion. And remembering back to Aristotle, is there a continuous force necessary to keep an object moving? Not if you don't have other forces involved. If there's only one force involved or no forces involved, then it'll roll forever. It moves forever. Okay? However, as you see on the thing there, eventually we say it'll stop. Why does it stop? Because you have air resistance pushing against it and you have friction with the floor pushing against it. Those are opposing the motion. Your initial applied force that you had to get it rolling is no longer there, so all your forces are opposing the motion. Ultimately, it'll stop. Okay? But if you had a net force that was an applied force that was exactly equal to the resistive forces, the air resistance and the friction on the floor, then the net force is zero. So if it was rolling, it now moves at a constant velocity. Now, why do we say constant velocity? Well, remember back what our definition of force was? Oops, there it was. A push or a pull capable of changing an object's state of motion. Okay? So a force is required for something to change its state of motion. That's either to speed up, to slow down, or to change its direction. Any one of those is a change of motion. A force is necessary for that. So if you have no net force, in other words, the applied force is equal to the resistive force, your net force is zero, so if it's moving already, there's nothing to change that motion. So that's why natural motion is no net force to keep it moving. Now that brings up another idea, and that is the concept of inertia. Now we're going to return to this a little bit later, but this is on the right-hand column of page 34 or possibly page 2-10, okay? Galileo called the behavior of matter that causes it to persist in its initial state of motion to be inertia, the measure of an object's tendency to resist changes in its motion. Now, that includes at rest. If something's at rest, it's going to tend to stay at rest unless you apply a force to it. There has to be some force applied. Or if it's rolling in a straight line, it's going to continue rolling in a straight line unless some force makes it stop. Why does it stop? Air resistance or friction with the floor. Those would be the reasons it would stop, not that it required motion to keep going. Okay? Seems sort of like a circular argument, but that is inertia. So if I were to roll a ping pong ball across the table, it probably is not going to go all that far. Hey, we got Jason here.
Yeah.
Welcome.
Howdy.
Did you have any trouble getting here?
Not really.
All right, good deal. Glad you could make it.
Yes, sir.
Okay. Where we are, we're in section 2.3 in your text. I don't know if you've got it handy, page 34 on one numbering or 2-10 on the other numbering, however you choose to look at that. And we were just talking about in the absence of a net force, motion is constant. Okay? If you have a net force, your motion is going to change. Either speed up, slow down, or change direction. The tendency to resist a change of motion is called inertia, and that would even include rest. An object at rest tends to stay at rest unless it's acted on by an unbalanced force, but an object that's moving tends to keep moving in the same direction, same speed, same everything, unless it's acted on by an unbalanced force. Inertia is that tendency. I was just going to say, if I had a ping pong ball and I rolled across the table here, more than likely it's going to slow down pretty fast because it's very susceptible to air resistance. It's so light, has very small inertia. However, if I rolled a bowling ball across the table, it's going to keep rolling pretty much at the same speed until it falls off the table because it has a large inertia, large tendency to resist changes in its motion. So that's what inertia is. Okay? We're going to have some further examples of this coming up a little later. Okay. Here are, and I can't read the whole of the slide here, it's something about balanced and unbalanced forces. It's basically what I've already been saying. Motion continues unchanged if you have no unbalanced forces. Now, if you do have unbalanced forces, it's going to change your motion. And before we get to this example, let me go to another one. If you can imagine an airplane flying at 500 miles per hour, straight line motion, level flight, 500 miles per hour, what do you think the net force acting on that plane is? Large, small, what? Anybody? Net force acting on the plane. 0. Now, does that mean there's no forces acting on the plane? No, it doesn't. Okay? It means the net force is 0. Because net force, remember I said level flight, constant speed, straight line motion. The net force has to be 0 because it's not accelerating. Okay? Surely the engines are still spitting out stuff out the back. That's what's moving it forward. But it's also hitting air resistance. At 500 miles per hour, there's a lot of air resistance. So those are balanced out. The net force is 0. You have gravity pulling down on that huge old plane, but the lift in the wings, I think we talked about this before with Bernoulli's equation, Bernoulli's principle, that's lifting the plane. So you have the net forces are 0. Whatever is pulling down, something else is pulling up. Whatever tends to speed it up, something else is slowing it down. Now, natural motion, about the only place you actually find it is in free space, way out there, outside of the gravitational field of anything else. That's absolutely natural motion. Constant velocity never changes. There's no air resistance against it. There's no gravitational force against it. Nothing. It's moving at a constant motion. What's the net force on it? 0, because there's no change of velocity, no change of motion. So natural motion in free space means constant velocity, constant speed, constant direction. However, if you did have a retarding force, like you fired some retro rockets, that would slow down that satellite, okay? That's changing its motion. That means there is a net force acting on, unbalanced force acting on the spacecraft. However, if you fired the rockets in the other direction, that would increase the speed. The boost needed to increase the speed, and that's a change of velocity because it is a increasing of speed. However, you could have the force perpendicular to the motion, and that's not going to change the speed at all, but it will change the direction. And if you recall, velocity is a vector quantity. Anytime you change direction, you're also changing the velocity. And a change of velocity is an acceleration. Acceleration is caused by net force. Okay. So, as they say here, the motion continues unchanged without unbalanced forces. However, if you have a retarding force, it decreases speed. A boost increases its speed, and a sideways force changes the direction without necessarily changing the speed. Now, there's sort of what I consider a dumb little blurb at the top of the right-hand column of page 35, missed mistakes and misunderstandings. It says, do you get wetter if you walk in the rain or run in the rain? Okay? If the rain is constant, basically it depends on how long you're out there. If running in the rain gets you to your destination sooner, you get wetter walking. However, the distribution may not be the same. If you're running, more than likely, more rain will be hitting you in the face, in the front. You'll get wetter in the front, drier in the back. So it's sort of a dumb little blurb there, so it's not worth spending too much effort on. Some of them are quite good. This one's not one of those. But we're moving on to 2.4, which is on page 35 or 2-11 in your text. And here we're talking again about straight line motion, but this time it's vertical, not horizontal. Earlier we were talking about horizontal motion, okay? Here we're talking about vertical motion, falling objects. Now, what we didn't take into account with horizontal motion, and we didn't need to, is gravity is always pulling down on that ball, but the table or the floor or whatever the surface is pushing up on it. Net force 0 in those directions. Okay, that's why we didn't even measure it. However, in vertical motion, gravity is always acting on that object. This happens to be, what is that, the number 10 pool ball, I believe, or 13 maybe. Now, I should have told you this. Can you hear me now? Probably not. Can you? You still can't. Okay. Oh, wait. They've removed the 40-minute time limit on our group meeting. So normally, since this is the free Zoom, usually it's a 40-minute time limit. They're letting us keep going. So thank you so much. Okay. So we can keep going. Otherwise, on other days, if they don't remove those, then I'll have to log out, get you a new passcode, put it back on Blackboard, you enter that, and you get back into the meeting going on. So today, they let us go without it. Thank you. Okay. So let's talk about falling objects. This is not a picture of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 pool balls falling down here. This is one pool ball, but this is a picture taken from a camera that has a perfectly open aperture. Completely open, but it's in a perfectly dark room. And the only thing that's changing is you got a strobe light. I think it's every 100th of a second the strobe light comes on. That's the same pool ball, just seen at different, at tenths of a second or hundredths of a second interval. What you see happening here, the displacement is less at the beginning, is greater, 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 all the way down. So it's increasing its speed, okay? but it's increasing the speed as a constant rate, which means it's a uniform acceleration. And this also was part of today's lab, which we're not having. We'll see if we can get it done in the future, okay? Now, here's a kind of bizarre thing about this picture. I believe the ball is being dropped from above. Initial velocity is 0, and it's being pulled down by the acceleration due to gravity. Constant acceleration, increasing by a fixed rate every time. However, the same picture, if you had been good enough to throw the ball straight up with just the right speed, it would look identically the same, because it would be slowing down as it went up. It would be hard to get it to stop right at the top, easier to drop it from rest right at the top, but the picture would be identical, okay? There's a little concept supplied on page 36, that's other page 2-12, on falling bodies, and this is actually something that Galileo came pretty close to doing, but you can, if we were in class, I'd do this right in front of you, but you can read that, do it on your own. You'll see that's the case. They have a blurb here to come up with a formula. Here they're just going to give you the formula, okay? The distance an object has fallen is 1/2 the acceleration of the object times the time it's been at that acceleration squared, okay? That is the formula for distance. Now this is a very special case formula. Two things are assumed here. And first is your initial velocity is 0. If you drop the ball, then this is what it does. If you threw the ball, you have to have another term in there for initial velocity. Secondly, your initial displacement is also 0. So if you were to start at the top of a hill somewhere and drop something, then your initial displacement would be way up there, not at the bottom. So this is assuming your initial displacement is 0 and your initial velocity is 0. Now I'm going to give you the formula in case they're not. D is equal to 1/2 AT squared plus VIT plus DI, where DI is the initial velocity, VI is the initial, DI is the initial displacement, VI is the initial velocity. Your A is your constant acceleration. Again, we're talking about uniform acceleration. Okay. There are a couple of figures in the book. I think they're going to show up on the slide. Let's see if they do. Okay. I think we'll get to them here. A little definition here. What do we mean by free fall? That means an object is falling under the influence of gravity alone. No air resistance. Do we ever have this on the surface of the Earth? No. There's always some air resistance. However, air resistance is proportional to the velocity. So if the object is falling slowly enough or coming down slowly enough, then we can ignore the air resistance. Okay? And that formula we just had said the distance is proportional to the time squared. Let's see if it shows up here too. Yeah, there it is. The distance is proportional to the time squared. We could have written this D is proportional to time squared. Okay? And the constant of proportionality here would be 1/2 A. Okay? To make it an equation. You don't have to know that. That's just there. Okay? Now, the distance increases by the square of the time. The speed increases linearly with time. V is equal to AT, not T squared, AT. Okay? Let's see if that formula is here too. No, I don't think so. Okay? Now, and this is what I was talking about before, trajectories exhibit up and down symmetries. And that's what I was talking about with this. If you had thrown the ball upward, straight upward, with exactly the right initial velocity, it would go up, touch the thing at the bottom, and then come back down. The picture would look identically the same. You can't tell if this was thrown up or released from rest. I almost guarantee you it was released from rest because it's really hard to get it to stop right at the top. That's what they mean by trajectories exhibit up and down symmetries. The acceleration is the same for all objects. Unlike what Aristotle said, Galileo and Newton agreed the acceleration is the same for all objects. Okay. Now, let me clear some of the stuff off of here. Okay. Here is an example of how far the object falls after a given number of seconds. Sorry. In 1 second, it only falls 4.9 meters. How do you get that? The acceleration here, free fall, and this is in SI units, metric, this would be 9.8 meters per second squared. That is the acceleration due to gravity. They haven't given it to us yet, but it will be. That's where that comes from. So your acceleration is 9.8 meters per second squared. So in 1 second, you have a 1 here. You have half of 9.8 is 4.9. In 2 seconds, put a 2 in there, it's 2 squared is 4, half of 4 is 2. 2 times 9.8 is 19.6. So it's gone 4 times as far as it did in 2 seconds as it did in 1 second. It's not a linear relationship. It's a squared relationship. And in 3 seconds, that's the one they had here. Okay. 3 squared is 9. 9 times 9.8 divided by 2. Oh, actually, 1/2 of 9.8 is 4.9. Multiply that by 9, and you get 4.1. So it's gone 8 times further than it did at the very beginning in 1 second. And if you let it go 4 seconds before it hit the ground, it will have traveled 78.4 meters. That would be quite a bit more. All right. However, if you look at velocities, not distances, you'll see that it increases its speed at the same rate every second. 9.8 seconds, and here's your formula. B final is equal to A times T. So when that T is 1, that was 9.8. When it's 2, it's 19.6. When it's 3, it's 29.4. When it's 4, it's 39.2. So speed increases linearly with time, increases by the same amount every second. Distance increases by the square of the time, so it increases much more every second. Okay. Now, that was 2.4. Before we leave 2.4, let's back up and clear my screen here. And let's do example 2.7. A rock that is dropped. What does it mean to drop something? In physics, what do you pay attention to? The deal is that means the initial velocity is 0. You see, if you threw something, then you give it an initial velocity. When you drop something, you just release it, so its initial velocity is 0. So that's what that word means for you. A rock that is dropped into a well hits the water in 3 seconds. So that's your time interval. Delta T is equal to 3.0 seconds. If you're able to ignore air resistance, which you sort of can now because in 3 seconds not picked up that much speed, how far is it to the water? So we're looking for distance. That's the unknown here. Well, what's our formula? D is equal to 1/2 AT squared. Your initial velocity is 0. We said that. And initial displacement is 0. Okay? So it's 1/2 I don't know what that, oh, there it is. Okay. Let me erase this then. Okay. So our formula, that's what I had it back there for, 1/2 AT squared, where A is 9.8 meters per second squared, the acceleration due to gravity. D is equal to 1/2, I'm going to go and write it as GT squared, where G is the acceleration due to gravity. So that would be 0.5 times 9.8 meters per second squared times 3.0 seconds. Okay. Well, half of 9.8 is 4.9, and then multiply that by 9 and you get 81. 12 and 8 is 20.1, I think it is. And here you have square seconds. Here you have per square second. So it would be 4.9 meters, okay? Because your seconds canceled out. No, wait a minute. I forgot 3. 3 times, I can't add. 3 times 9 is, no, I'm sorry. I had it more right the first time. Sorry about this. Okay. All right. All right. Sorry about that. 9 times 9 is 81. Carry the 8. 9 times 4 is 36. With 8 is 44. 44.1 meters, because your seconds canceled, square seconds canceled out. So that's what we got. And that was the same thing we saw here. This one. Whether you're dropping a rock from the top of a building or dropping it into a well in 3 seconds, whatever you're dropping is going to travel about 44.1 meters in those 3 seconds. It doesn't matter what the material is. Okay. That was example 2.7 on page 38. Now, one thing to note in the book, they have 2 significant digits here, 2 significant digits here. 1/2 is exactly an exact number. So they rounded to 2 significant digits. Count 2 digits. Look to the right. It's less than 1, so leave that alone. So 4.4 meters. Right. No, 44 meters. Sorry about that. The old gray cells aren't working well today. 44 meters. They dropped the 0.1 because it was too many digits. All right. Okay, that was solution 1. Solution 2 is another way to go about doing it. It's longer to do. I don't see any reason to do it, but you can take a look at it and see what you get out of that. All right, so there we've had horizontal motion, one-dimensional motion horizontally. We've had vertical motion, one-dimensional motion vertically. Now we're moving to compound motion. This is 2.5, and this is, like I said, 3 types of motion. They first mentioned horizontal motion in 1 dimension, horizontally, 1 dimension vertically is 2, and then number 3 is compound motion, which is a combination of 1 and 2. This would have been the lab for Thursday. aren't going to be there Thursday. So anyway, if I can find something that I put out there, you can probably do 2 labs at one time. They're going to be very short. Okay, it's a combination of horizontal and vertical motion. Now, sometimes we call this projectile motion, because if you are this comes from military application, firing a projectile at an enemy, say. You're going to fire it into an arc. It goes up into the air and comes down, hopefully hitting them. Any object you throw into the air, baseball, basketball, football, any object you throw into the air, that is, usually compound motion. You have a vertical component and a horizontal component. Okay. Here are your basic observations on it. Number 1, gravity is always acting on the object. It's acting on the object on its way up. It's acting on the object on its way down. It's acting on the object when it's at its peak. Gravity is always acting on the object in a uniform manner. Number 2, the acceleration, g, is independent of the object's motion. Like I said, whether it's going up, whether it's coming down, whichever it is, it doesn't matter. The acceleration due to gravity is independent of the object of the motion. Okay. Now, seems like they're kind of doing backwards here, but they're really not. If you were to throw an object straight upward, this is now going back to vertical motion only. Vertical projectile, you throw it straight up into the air. It slows down every second that it's on its way up. How much does it slow down? 9.8 meters a second every second, or 32 feet per second every second. That's just what it does. Okay? However, if you were to, sorry, I'm having trouble breathing. I'm sort of getting clogged up. I think it's pollen and stuff. If you were to throw something straight up, it's going to slow down on its way up. It stops at the peak. Now, it depends on how fast you throw it. Throw it really fast, it goes way, way, way up there, but at some point it stops and then comes back downward, picking up speed at the same rate that it lost speed going up. That's what we mean by, what was the term they used before? Symmetric. The motion is symmetric going up and down. Now, the force of gravity acts downward throughout the process. Force of gravity never pushes something upward, always down, pulling it down. Now, what if you could fire an object perfectly horizontally? The horizontal component of the velocity would remain the same throughout the motion. That's ignoring air resistance, neglecting air resistance. I guess that's all I got on that. Yeah, I guess what they're saying at the end here, if you throw an object up, not straight out, but any other, in fact, straight out actually works this way too, because the gravity is always pulling it downward, you always are going to have a curved path. Always. Straight up won't be curved necessarily, but anything that's off the vertical is going to have a curved path. Even a straight line horizontal shot is going to move down. Either of you play baseball? if you ever notice it, the pitcher's mound is always a little bit elevated over the batter's box. Why? No matter how hard that pitcher throws, the ball's going downhill. Gravity is going to be pulling it downward. Okay? Not a very long distance for it to do, but it always is pulling it down. Now here's one of the strangest illustrations of this. If you have the gal up here firing a perfectly horizontal arrow and shooting it somewhere way out there, you have the guy here holding an arrow. If he releases it at the same instant she releases the bowstring, the arrow hits the ground at the same time. Not at the same place, nowhere close, but at the same time, if it's nice level ground. Now if she's standing on a hilltop, it's going to take longer, or if she's shooting up a hill, but as long as it's flat level ground, they will hit the ground at exactly the same time. Okay. Now, let's see how our time is going. 2:28. We're about halfway through probably what we're going to get done today. Oh, not quite. Oh, getting close. My throat's getting a little dry. I'm going to take a quick break here, and I can't stop the Zoom, but I will stop this. I just need to run and get a glass of water. I didn't bring one in here. So I'll be back in less than 5. All right, I'm back. Sorry, I just needed something to wet my whistle. They give the example here of passing a football, and that's over on page 41 is where the picture you'll see. I was just looking at these other figures here before you get there. On page 30, let's see. Yeah, on page 39 is the same sort of one that we saw earlier, vertical motion, that one, except this one you really can't tell if the ball's coming. Well, actually, I think so. I think this one was probably thrown upward and went right past the thing because you see a little shadow in the background. But you can't tell looking at it whether this is going down or going up at all. The next picture there, figure 2.15, it shows a guy throwing a ball up and a boy up in a tree, it looks like, dropping something. If the guy would have thrown the ball up exactly the height of the tree, the boy on the tree, and the boy would have dropped at the time it peaked, they would have hit the ground at the same time. And it would have taken twice the time as the guy that threw the ball up and come down. Again, symmetric trajectories. Okay. And then throwing the football, this is on, the talk is on page 40. Sorry, my throat's clogging up again. The figure is on page 41. And that's this one. Okay. Now, throwing a football, or any ball, a basketball, a volleyball, a tennis ball, hitting a golf ball, it doesn't matter. The only force after it's left your hand or left the ball, the bat, left the tennis racket, left the golf club, once it's no longer in touch with them, the only force acting on that ball is gravity, and it's always pulling it straight down. Straight down. The vertical velocity, if you're throwing the ball upward, passing the football upward, vertical velocity is decreasing, stops, and then increasing, coming down. Okay? Horizontal motion is uniform, always uniform. And the combination of those two forms the shape we call a parabola. So here is what they're talking about. And you see when you throw the ball up, its initial velocity has a pretty long vertical component. It reduces until here it's absolutely zero. Here now it's slightly down, more down, more down, okay? However, the horizontal component is exactly the same throughout the path of the ball, and that gives it the parabolic shape, okay? No matter what you're doing, throwing a football, kicking a football, hitting a baseball, throwing a baseball, it doesn't matter. The only exception to this is dunking a basketball. That's not a parabolic shape, it's just going straight down. I don't do that, never have, never will, okay? So I don't even include that, okay? But that's what gives the shape of that, okay? Sometimes these quarterbacks think they can throw a beeline, a straight thing, and when they do, the ball always has to be an awfully good receiver to be able to pick it up right off the top of the ground, okay, because that's where it's going to head, okay. Now we're moving to section 2.6, the 3 laws of motion. Now the 3 laws were first detailed by Newton. However, Galileo had already come up basically with the first law, okay? But Newton perfected it, did a little bit more to it, and then gave some of the reasons for it. Basically, Galileo just observed it, measured it, and saw that it was happening. Newton gave a bit more detail for it. So the 3 laws were first detailed by Newton. He lived from 1564 to 1642, which if you look at that, 78 years back in those days, that was a long life, okay? Brilliant individual. I mean, there have been few minds anywhere close to his mind ever existed on the planet. Not only did he come up with 3 laws of motion that basically became our, oh, Chad's back. Welcome back, Chad. That came up with the 3 laws of motion, which basically all of physics is based on. He also, in order to do that, had developed an entirely new branch of mathematics to explain that motion, okay? And that was calculus, okay? Not only that, he came up with an entirely new concept of the law of gravitation. Not only that, he came up with new concepts in optics. Just, I think even photoelectric effect. It was just amazing what he came up with. But for the 3 laws of motion, the essential idea was the idea of forces, okay? You'll see the force mentioned in every one of these 3 laws of motion. So let's go to the first one. Now this one, basically, the outline of it and everything was done by Galileo, okay? Newton read Galileo's work and expanded it and perfected it, okay? Often called the law of inertia, first law of motion. Every object retains its state of rest or its state of motion, uniform straight line motion, unless it's acted on by an unbalanced force. I've basically almost been saying that for much of the earlier part of this chapter. That's Newton's first law, the law of inertia, okay? Now, remember what inertia is? That characteristic of a material, of an object, to resist any changes of its motion. So an object is going to try to stay in its state of motion. If it's at rest, it stays there. If it's moving, it's going to try to stay moving in a straight line, unchanged, okay? That's Newton's first law of motion. Here's a few examples of it, okay? Now, if I'm moving through these slides too fast, let me know. I see you're taking a lot of stuff down. I don't know if you've ever been on a bus or possibly the trains in the airport in Atlanta or any of things like that, and you're standing there just tooling along, not paying attention, and suddenly the bus takes off. What do? You fall back. Well, you're not really falling back. You're trying to maintain your state of motion. The bus is moving out from under you. It's not that you're falling backwards. It's the bus is moving forward. Okay? That is basically what inertia is. You're trying to maintain your state of motion. I can remember one time, this was several years ago, my lawnmower, I noticed, wasn't going as long between gas changes, and I started looking into it. I found a little leak in the fuel line, and I didn't have the materials to change it, so I found a place that would do repairs, and I was going to haul it to them. So I put it in the back of my pickup, and I thought I chocked the wheels adequately. I didn't. The chocks moved or something or other. Every time I sped up, wham, it went into the tailgate. Every time I slowed down, wham, it ran into the cab. And when I turned one direction or the other, it moved to one side or the other. It was not a pleasant trip, but we got there and it was okay. But that's inertia. The lawnmower was trying to stay right where it was. I was speeding up the truck under it or slowing it down under it. It tried to maintain its state of motion, just like you do in a bus. Okay? That's Newton's first law. However, if the bus is moving along in a straight line, and this is true of cars too, and then suddenly makes a turn to the right, you say you're thrown against the left-hand side of the bus. No, you're not. The bus cuts in front of you. You're not thrown. The bus is moving in front of you. You're trying to maintain your straight line state of motion. It turns and you hit the side. Okay? That's what's happening. That's the law of inertia. Newton's first law. Now, what's the second law? Okay, go back to the first law. Every object retains its state of rest or its state of motion unless it's acted on by an unbalanced force. Okay? If there's no unbalanced force, it maintains whatever it's doing. But if there is an unbalanced force, it changes its motion. That's Newton's second law. Forces cause accelerations. Okay? Now, the formula for that, I think they're going to show over here. There it is. The net force acting on an object is a product of its mass times its acceleration. Now, mass is related to the inertia, what we were talking about before. The larger the object has more inertia, smaller object has less inertia. The acceleration, that means change of velocity. That means change of motion. The only way an object has a change of motion is accelerate. If it's accelerating, that means there's some net force acting on it. Forces cause accelerations. Accelerations result only from forces. Okay. Now, what are the units for force? Okay. What I just did, but it made a noise. What's the unit for mass? The SI unit for mass. Anyone remember? On your first test, I think y'all did fairly well on it. Kilogram. Not gram, kilogram. Only one that has a metric prefix. Acceleration, you remember what that unit was? I've already hit it at least once today. I don't know if either of you were still here then. It's meters per second squared. Change of velocity per change of time. Velocity is meters per second, meter per second squared. So a kilogram meter per second squared, this is called a Newton. Guess what? Named after Sir Isaac. Okay? That's named a Newton. Okay. Now, you'll notice kilogram is not capitalized. Meter is not capitalized. Second is not capitalized, but Newton is. I wonder why. It's named after somebody. A kilogram isn't named after anybody. A meter is not named after anybody. A second's not named after anybody. A Newton is. So units that come from a person's name are usually capitalized. Okay? So that's what a Newton is. A kilogram meter per second squared. All right. The proportionality constant, what we were saying up here, forces are proportional to your acceleration. What is proportionality constant? Equal K. That K is the mass. Okay, equal K replaces proportional to. The proportionality constant is the mass. Now, if you have an object with constant mass, which you usually do, if you exert more force, you exert a greater acceleration. Or if you accelerate it more, it requires more force. However, if you have an object with a constant force acting on it, and you increase the mass, the acceleration goes down because the force is constant. On the other hand, decrease the mass, you increase the acceleration. Now here's the examples that sort of show this. And okay. Nope, didn't show it. Oh yeah, well I think it'll show up in a second here. The more mass, well, we're missing a slide. If you, let me clear this out of the way. If you look in your text on page 42 or 2-18, at the top of the right-hand column, you'll see figure 220, a guy riding a bicycle, and if he's exerting a certain force by his pedaling, and there's a certain frictional force, both air resistance and road friction, then if those two are balanced, he's going at a constant speed. Even though he's exerting a force, the net force is zero. Net force is zero means constant speed. Zero acceleration means constant speed. Doesn't mean zero speed, it means constant speed. Okay. Now, if you then, and the picture on page 43 shows the guy on a tandem bicycle, a bicycle built for two. If then his girlfriend gets on behind them, just assuming she has the same mass that he does, he's either got to pedal harder, in other words, increase the force, or decrease his acceleration. So more force would be more acceleration. That would be the first picture. More mass means less acceleration unless he increases his force. Okay? Now, I don't know what more mass, less acceleration again means. That's all the pictures we have. So there must have been something else they had in mind. The focus here is on what they call the net force. Now, I'm trying to figure out what they mean here. Here we go. Here's the guy on the bicycle, okay? If he is pedaling along, exerting a force that's moving the bicycle forward, that's the applied force. He's hitting resistance, friction with the road and friction air resistance, both of those. Now, if he's sitting up like that, he's got quite a bit of air resistance, especially if he's going very fast. He's not very streamlined. But these two, if he's going at a constant speed, that means these two have to equal the applied force. Otherwise, it wouldn't be a constant speed. If he doesn't have enough applied force, it's going to be slowing down. If he has too much, it's going to be speeding up. This is saying the applied, this is not right. The net force is zero. The applied force is not zero, the net force is zero, because the sum of the applied force and opposing forces are the same. Okay. Now, and again, the focus is on the net force. Net force is zero in this case. That's what this is talking about. The air resistance and tire friction exactly match the applied force. The result is no acceleration, which means does not mean no velocity. It means constant velocity. Zero acceleration means constant velocity. Now, that velocity may be zero. That could be, but it doesn't mean necessarily that you're not moving. It's just that you're not increasing your speed. All right. Now toward okay. Before we get to weight and mass, let's back off and use this space here to do a couple of examples. 2.8 and 2.9. They seem to like bicycles here. A 60 kilogram bicycle and rider. What does 60 kilograms measure? What unit? Not listening, huh? Kilogram measures mass. Mass is 60 kilograms. Now this is mass of the bicycle and the rider. It accelerates at 0.5 meters per second squared. That's a good unit for acceleration. How much extra force was applied to make it accelerate? So your net force has to be increased here. The net force is mass times acceleration, which would be 60 kilograms times 0.5 meters per second squared. That's basically half, so that is 30 kilogram meter per second squared. Okay? And what is a kilogram meter per second squared? That is a Newton. 30 newtons. Kilogram meter per second squared is the same as a Newton. Okay. All right. That was example 2.8. Let's move to example 2.9. What is the acceleration? This time acceleration is the unknown. What is the acceleration of a 20 kilogram cart? What does 20 kilograms measure? Do you know? Not listening. That measures mass. Okay, 20 kilograms measures mass. If the net force on it is 40 newtons, so the net force here is 40 newtons. Now, in a problem like this, I would change the newton to its fundamental units. Okay, well first, let's figure out what formula we use. Net force is equal to mass times acceleration. The same one we've been using here. Net force is mass times acceleration. Okay, but this time we're looking for acceleration, so let's divide both sides by mass. Okay, so acceleration is equal to the net force divided by mass. Now what I was saying is let's not use newtons, let's use 40. What is a newton? A kilogram meter per second squared. Divide that by the mass of 20 newtons. 20 kilograms. Okay, keep your units. Okay, 20 will go in the 40, 2 times. Kilograms cancel out, you get meters per second squared, a great unit for an acceleration. Meters per second squared, 2 meters per second squared. I'm sorry, I erased the first one. I didn't even, yeah, we got 30 newtons. I didn't check and see what the book got, but they got it right too. Okay. Now, there is a second law experiment that they show here. And this would have been pretty close to our fourth law, I think, okay, when we talked about net forces, a second law experiment. Unfortunately, we'd have to be together to do it. We're not going to be together, so I'll try to come up with something else. Okay. So you can read that if you'd like. If you want to try it, you certainly can. Okay. So let's move to weight and mass. Now, a lot of times in everyday English, we use these two terms as if they're the same. In fact, if you go to most grocery stores, okay, and look at the scales there in the produce department, they'll usually have weight on the outer ring and in pounds, and then they'll have kilograms on the inner side, as if they're measuring the same thing. They are not. Weight is a force, mass is mass, okay? Mass is a quantitative measure of inertia. I mentioned that before, a measure of inertia. Basically, it is the amount of matter you're dealing with, okay? What weight is the force of gravity acting on the mass or the object, okay? Okay. Now, so weight is a force, pound measures forces, kilogram measures masses. Pounds and newtons are equivalent measures. They aren't the same numbers, but they're both measuring forces. Kilogram, though, measures mass, and I think I asked this in the last class. I don't know if any of you remember what was the unit of mass in the U.S. customary system. Does anyone recall? Okay. What that is a slug. Okay. No one uses the unit slug. Have you ever gone into a grocery store and said, I want 3 slugs of potatoes, please? No, you wouldn't use that terminology anywhere. Okay. So we act as if pounds and kilograms are measuring the same. They're not. Pounds and newtons are both measuring forces. Kilogram measures mass. Now, why can we get away with drawing our scales with both numbers on them? Because they differ by a constant. The acceleration due to gravity is constant anywhere on the surface of the earth. Top of Mount Everest, bottom of the Dead Sea Valley, okay? The acceleration due to gravity is basically the same. So weight, which is a force, is m times g, mass times acceleration. Just like, now, these aren't doing the same thing, but the formulas are similar. This is net force is equal mass times the acceleration. That's a net force acting on the object. This is the force due to gravity, weight, okay? Those are not the same thing, but their formulas are very similar, okay? They're both measured in pounds or newtons. Mass measured in kilograms or slugs, and acceleration measured in meters per second squared in the SI units. If you're in the U.S. customary, it's 32 feet per second squared. But the G here, acceleration due to gravity in the SI units is 9.8 meters per second squared. Okay. So the reason the scales can be the same is that it's a constant that separates the two. It's a dimension constant. This is in meters per second squared. This is just in kilograms, so this would be in kilogram meter per second squared. Okay. Now, before we get to the third law of motion, there is a table at the top of the right-hand column on page 44 or 2-20, and it shows it does not use the unit slug. It calls a slug a pound per foot per second squared. Strange way to express it, not even using the name. Okay? Acceleration is feet per second squared or meter per second squared. The force is in pounds. Or in the SI units, newtons. Okay. I guess we're ready for example 210, if my voice will hold out. I've been talking pretty much solidly since 8 o'clock this morning. Talking. I've had other conversations otherwise later, but I have very little time in between each of the classes, so I'm about spent here. Let's do example 210. Let me see if I can find. Okay, let's do it here where we did the last ones. Okay, what is the weight? So here we're looking for little w, weight. Later we'll see capital W stands for work, so don't confuse those. Little w is weight. What is the weight? That's the unknown here. Of a 60 kilogram person, 60.0 kilograms. What's that a measure of? Do you know? Mass. 60 kilograms per kilograms measures mass. If that person is on the surface of the earth, what does that tell you? One thing we're missing here, W is equal to, what's the formula? Let me erase this. W is equal to mg. What are we missing? G, which is 9.8 meters per second squared. So, since you're on the surface of the earth, G is equal to 9.8 meters per second squared. Anywhere else in the solar system or in space, it's going to be different, okay? The moon, about 1/6 of that. Jupiter, if you could stand on the surface of Jupiter, way, way more than that. Venus would be close to the same, but it's such an obnoxious place you wouldn't last very long. Mercury would probably be right around the same as the moon, about 1/6. So it's a mess out there, okay? So what is weight? Weight is mass, 60.0 kilograms, times acceleration due to gravity, 9.8 meters per second squared. And if you multiply those together, you get a 48. $54 and 4 is 58. Whoops. 48. 54. Yeah. I don't know why that came up. There we go. 588 what units? Kilogram meter per second squared. That's also a Newton. Okay. Now, almost guarantee you that's not the answer they give in the book. And here's why. They only have 2 digits here, so I think they say approximately 590. I'm trying to remember for sure. Yeah, they round it to 590. I'm happy with 588. You don't have to round just because of that. In fact, some books list this as 9.80 meters per second squared. This one just doesn't. All right. Now, example 211 is that same 60 kilogram person, but now that person is on the moon. And their weight on the moon, W on the moon, this is weight on the earth, weight on the moon is 100.0 newtons. And this is what I'm looking for is all right. What is the acceleration of gravity on the moon? So here's your formula. Can't believe I didn't write it down. I didn't write it down. Weight, oh, I know what I did. I went back here. Right here, I circled it. weight is equal to mass times acceleration due to gravity. Well, we're looking for G on the moon. That's the unknown here. And we know that weight is equal to mass times acceleration due to gravity. And since that's what we're looking for, we'll divide both sides by mass. And you have G on the moon is the weight on the moon divided by can't get my pen to write well, divided by m, and that would be, there it is, 100.0. Now I'm not going to write it as newtons. I'm going to write it in basic units, kilogram meter per second squared. That's what a newton is, divided by the mass of 60 kilograms. I can't write 60 kilograms. Okay, so pull out your handy dandy calculators. 6 will go into 10 one time. 6 will go into 46 times. Something like 1.67. And the kilograms cancel out, meters per second squared. I think that's what they get. They got, yeah, 1.67 meters per second squared. All right. Whew. Okay. All right. Now, what? Sorry. Hold on just a second. I brought my water in here because I'm getting so dry. Okay. That's mass and weight. That was example 2.11, top of page 45, or 2-21. Okay. Moving from that, we go to Newton's third law of motion. Obviously, this guy's a football fan. He had throwing a football. Now he has Arizona State. This guy was from Arizona, probably teaches at Arizona State. Let me see. I think that's true. Yep, Arizona State University. No wonder he has them in there. Okay, what is Newton's third law of motion? A little bit of a review here. The first law, an object doesn't change its state of motion unless it's acted on by an unbalanced force. Second law, if it is acted on by a net force, an unbalanced force, it accelerates. That's changing its state of motion. The third law is a little bit different. And here's one way. The source of the force is another object. I think I read or heard somewhere that Newton said it this way. If I push my finger against the rock pushes against my finger. And if you pull your finger back from pushing on a rock or the edge of a table or something like that, you see your finger has got a little dent in it, okay? That's because the rock pushed on your finger as well. So the source of a force is always another object. So Newton's third law, a little bit different from the other two. The other two were all talking about an object in motion, an object at rest, the net force on an object, on one object. The third law relates forces between objects. There's always a second object involved, okay? And here's how you state, one way of stating Newton's third law. Whenever two objects interact, the force exerted on the one object is equal in size but opposite in the direction to the force exerted on the other object. Okay? Now, don't get the two different concepts here confused. Newton's second law, net force on a single object is mass times acceleration. The third law talks about the force on one object, force on object A by object B, or the force on object B by object A, and that these two are equal but opposite. Okay? Whoa. That's all they write about that. There is in your book, and let's see, I don't think they give you a place to write it. I'll try to write it here. An equation that relates this, and it's what I just said. I don't have much room to write, so I'll try to squeeze it in down here. The force on object A due, that's pretty ugly writing, to object B is equal but opposite, okay? And they don't put the minus sign there, I put it in. They're talking about magnitudes here, so let's just talk about magnitude. Force of B due to A, okay? The force on object A due to object B is equal in magnitude to the force on object B due to object A. Now, the next slide is going to relate to this big time, and I'm real tempted to wait and use the example there, but I think I will use it here as well. If you've ever stepped off of a lightweight aluminum fishing boat, but your buddy wasn't holding it tightly against the dock, then when you pushed off there, the boat took off and you went into the water, or almost, okay? Not a pleasant feeling, okay? However, when I was in the Navy, I stepped off an aircraft carrier and I didn't budge the thing. Well, guess what? The forces on either case were the same. It's just that the little bass boat has way less mass than the aircraft carrier, so its acceleration was huge compared to the aircraft carrier, negligible acceleration, okay? So, but the forces are exactly equal. The force of which I push off the ship is pushing off of me, okay? And that leads to the concept of momentum. Oh, wait. There is an example. Let's go back. I hadn't turned the page far enough. Okay, let's go to page 46, example 212. So let's go back here. I think we're going to have to go back to this area that we've been doing all our exercises in, or examples in. A 60-kilogram astronaut, okay, I hope you know what that unit measures, kilogram. What does kilogram measure? Mass, absolutely. I can't hear you, but I see your mouth moving, okay? Is freely floating, I can't say that, freely floating in space, and pushes off pushes on a freely floating, this is mass of the astronaut, 120.0 kilogram spacecraft. This is the mass of the spacecraft, okay? And he pushes with a force of F on the spacecraft by the astronaut of 30 newtons, 30.0 newtons, for a time interval, delta t, of 1.5 seconds. Okay. The A part of this problem. Compare the forces exerted on the astronaut and the spacecraft. So the force on the astronaut. Well, guess what? These are two different objects. The only force involved here is the astronaut pushing on the spacecraft, which of course means the spacecraft pushes on him, these two forces are equal but opposite. If the astronaut's pushing on the spaceship to the right, the spaceship is pushing on the astronaut to the left. They're an equal amount but opposite directions. Okay? Okay? So that's the A part. Those two forces, the magnitudes are exactly the same. And since the force on the spacecraft is, so we're just going to talk about magnitudes, we're not going to talk about direction, it's equal to 30.0 newtons. The force on the astronaut is also 30.0 newtons. The magnitude, the amount of the force, they're equal and opposite. Okay? The B part of the problem, compare the acceleration of the astronaut to the acceleration of the spacecraft. Well, the acceleration of the astronaut, well, let's get our basic formula down. Force on the astronaut is equal to the mass of the astronaut times acceleration of the astronaut. The force on the spacecraft is equal to the mass of the spacecraft times the acceleration of the spacecraft. Okay? What we're looking for is acceleration of both of them. So we'll divide both of these by the masses. Okay? So you get the acceleration of the astronaut is equal to force on the astronaut divided by the mass of the astronaut. Well, the force on the astronaut was 30 newtons. Now, I'm not going to write it as newtons. I'm going to write it as fundamental units, kilogram, meter per second squared. Divided by the mass of the astronaut, well, that was 60 kilograms. So the kilograms go out, and this is 0.50 meters per second squared. Okay, I couldn't read my writing there. Okay, let's do the same for the spacecraft. Acceleration of the spacecraft is force on the spacecraft divided by the mass of the spacecraft. Force on the spacecraft is exactly the same. 30.0 kilogram meter per second squared divided by the mass of the spacecraft was 120 kilograms. Okay, so that leaves 0.75 meters per second squared. No, 0.25. Goodness gracious. Where's my math? 0.25, 1/4. Okay, now that's making sense. The more massive spacecraft, the less the acceleration for the same force. The less massive astronaut, the greater the acceleration because of the same force. And since the mass was exactly half, the acceleration is exactly double for the astronaut. Okay, so that's, now in the text, they had 3 significant digits everywhere, so I should have put one more 0 there and one more 0 there. I wasn't keeping up with significant digits. Okay, and meters per second squared is exactly what you want. Okay, example 213. Same problem. After the interaction and acceleration between the astronaut and the spacecraft described in example 2-12. Oh man, I'm running out of energy. I didn't have time to eat a full lunch today, so I'm feeling it now. They both move away from their original positions. what is the new speed for each. So we have acceleration, and we have the force acting over a time interval. So what is your relationship between speed and acceleration? Now, I'm running out of room pretty badly here. So let's see if we can squeeze it in here. If you remember, V final is equal to, and when they first push, the initial velocity was 0, is equal to A times T. Okay? Here's your delta T, here are your various A's. So the final velocity of the astronaut is 0.500 meters per second squared times the time interval is 1.5 seconds. Okay, that'd be 500 plus, that'd be 0.750 meters per second. Okay, because this second cancels one of those seconds out. Okay, I've got to do the same for the astronaut, the spacecraft. V final for the spacecraft is the acceleration of the spacecraft times the delta T, which is the same, and that's equal to 0.250 meters per second squared times your time interval 1.50 seconds. Again, the second cancels one of those out, and you're left with 0.375 meters per second. Okay, so it winds up that the final velocity of the astronaut is exactly twice that of the final velocity of the spacecraft. Exactly. Okay. All right. That kind of wraps up 2.7, which incorporated all of Newton's laws. Okay? 2.6. So now we're moving to 2.7, which deals with momentum. All right. Here's what momentum is. It's an important property, closely related to Newton's second law, but I would say, yeah, it is very closely related to the second law, but it's also in many ways related to the third law. We'll talk about that also. This quantity involves the effects both of the motion, which is velocity, and with the inertia, which is mass. Both of those concepts are involved here. Now, just a little bit of an idea here. First, velocity is usually a vector quantity, making momentum a vector quantity. Now, if you think back, Newton's second law, and this is relating to the second law, that was net force is equal to mass times acceleration. Vector. So in that ways, these are really closely related. They both depend on mass, but this depends on mass and velocity rather than mass and acceleration. Whereas force is mass and acceleration, velocity is mass times velocity. Momentum is mass times velocity. I'm getting tired, I can't talk. Okay. Here is what separates these two. Well, let me back off and say this first. When Newton wrote his incredible paper, they wrote in Latin back then. All scientific work and stuff like that was written in Latin. which meant only the incredibly well-educated people could even read it. And in fact, they would be the only ones who could even come close to understanding it. But anyway, I don't read Latin. I don't understand Latin. I don't have any concept of Latin, much to speak of. But it's still well, my understanding, and this is why I started talking about this, I haven't read it, so I don't know, but my understanding is that when Newton was writing this paper, he didn't refer to forces or things like this. He referred to something he called the quantity of motion, not just the velocity, not just the mass, the quantity of motion. And from my understanding is his quantity of motion was the mass, which involved and his quantity of motion involved mass and velocity. And I mean, I can't see any other explanation than he was talking about momentum. I don't think he ever used the word momentum. I don't know. I don't read Latin. But I think this is what he was referring to. So it seemed to me completely, almost completely irrelevant or wrong or something that they named the unit of force after Newton rather than the unit of momentum. That was his basic unit, was momentum, or what he called quantity of motion, which is a product of the mass and velocity. So anyway, that's what momentum is. Now, and by the way, we're also talking about linear momentum. There is such a thing as rotational momentum, and you can the lab we would have been doing, probably next Tuesday, would have involved the forces part that we talked about. Then it would have also involved the momentum part. And that part, you explained a little bit of what was happening by the rotational momentum of the object. Y'all are probably familiar with, the automotive students, with the concept of a flywheel. Flywheel has a lot of mass, and that maintains a very smooth ride, momentum. Also, when you're dealing with tires, you have to make sure that your angular momentum is fairly constant. That's why they put the little weights wherever they need to make sure the tire is balanced well. So those are both applications, you might say, of rotational momentum. We're not talking about that here. We're talking about linear momentum. I wish we had time to do rotation too, but it's a little heavier and more involved. So we'll just talk about linear here. Okay. Now, the one other thing I was going to say, the advantage momentum has over force, and this may have been why Newton referred to it, momentum is always conserved. Always conserved. Later in the next chapter, I think it is, we'll talk about energy. Total energy is conserved, but not kinetic energy. Momentum is always conserved. So it's one of those special quantities called a conservation quantity, okay, for lack of a better word. So there's your definition of it. Now, my guess, and this is just a guess, this is how Newton probably expressed at least two and maybe all three of his laws of motion. He didn't do it in terms of forces or masses or acceleration. This is my guess. He did it in terms of his quantity of motion. And here's how I would guess he wrote his first law. Something like this. The time rate of change, and I'm just guessing at this, of an object's quantity of motion, think momentum, quantity of motion is always constant in the absence of unbalanced forces. It's so much, I mean, I've put some extra words in there. So much easier than saying it stays, if it's at rest, it stays at rest unless it's acted on, or if it's moving, it's straight line motion. The quantity of motion is constant. The rate of change of, the time rate of change of object quantity of motion, always constant, okay? Unless it's in this, as long as there's no unbalanced force, okay? Okay, or something to that effect, okay? First and second laws almost wrapped up in those two. And when I say that, let me show you what that would look like. The time rate of change, that would be change of momentum, quantity of motion, per unit time. That would be the change of mass times velocity per unit time. Well, mass is a constant. It doesn't change. So you could pull this out and you have mass times change of velocity per change of time. Well, what's that? This is acceleration. That's where Newton's second law comes from. This is what a force is, a change of momentum per unit time, okay? That is, I think, how Newton described it, the rate of change of a quantity of motion. Now, I don't know that for a fact. Like I said, I don't read Latin, and I wouldn't be able to understand it if I read it. But my guess, that's what he talked about. And by the way, acceleration is also a vector quantity. Okay, beat that to death. Okay. Remember that problem that we had with the astronaut and the spacecraft? Here we meet it again. The mass of that astronaut was 60 kilograms. We calculated its velocity to be 0.750 meters per second. Mass of the spacecraft was 120 kilograms with this velocity in the opposite direction of 0.375 meters per second. What was the momentum of the spacecraft? 60 times 0.75. Do the math and it comes out 45.0 kilogram meter per second. Now guess what? Force has a unit of it's a kilogram meter per second squared. We call it a Newton. Momentum has a unit of kilogram meter per second. We don't have a name for it, unfortunately. There is no name for it. That to me should have been called the Newton, but I don't make up the rules, okay? But the spacecraft had a mass of 120 kilograms with its velocity being in the opposite direction, but 3.375 meters per second. Multiply those together, you get the same momentum. The change of momentum of the astronaut is the same as the change of momentum of the spacecraft. Opposite directions, but the change of momentum was the same. What's that telling you? Momentum of the system was conserved. Initially, neither one of them were separated. Momentum of the system was zero. The astronaut pushes on the spacecraft, he picks up a momentum, spacecraft moves in the opposite way at an equal but opposite momentum, still the momentum of the system is zero. It's just that each one of them has a momentum in the opposite direction now, but they're equal and opposite. So that's why I say it relates also to the third law, okay? Because you have the equal and opposite effects on each other. Now, here's another illustration of conservation of momentum, okay? Now, I meant to say this one too. Now, let me back off a moment way back, okay, this reminded me. When we were dealing with vertical motion, and I said everything, what did they call it? How did they name it? I can't remember exactly the wording they used. Let me find. Yeah, trajectories exhibit up and down symmetries, okay? Especially when you're throwing something up or dropping something from down below. Here's a really bizarre, almost morbid application of that, okay? I don't know if you've seen, it happens more in other areas than it does here. But when some of the crazies get out there and celebrate something, they fire weapons into the air. Okay? Now what is happening if you fire a bullet straight up, okay, from a weapon, straight up, perfectly straight up. Now let's say the muzzle velocity of that bullet, I don't know what typical is, let's just say 500 meters per second. That may be way too fast, feet per second, something, miles per hour, something. Very, very fast. Okay, you fire it straight up into the air. As it goes up, it starts losing its speed as it goes up. Now, it takes a long time for it to reach zero, but it loses speed at the rate of 9.8 meters per second every second. So it takes a long, long, long time, but it's gradually slowing down as it goes up. At some point, it will stop, and then it starts falling down at exactly the same rate at which it lost speed going up, it's gaining speed coming down. So guess what the speed of that bullet is? If you haven't moved and you fired it straight up, guess what the speed of the bullet is when it reaches you again? The same as the muzzle velocity. Okay, there is some air resistance. It may be a little bit slower, but in effect, it's just like pulling the trigger against your head. You better move, okay, because it is deadly. And that's what's so crazy about firing any weapon into the air, especially if it's a crowd of people around. It's going to come down at the same speed that it went up, and it can cause death or dismemberment, or okay, whatever. All right, let's go back to where we were. Long time passing. Okay. So that's what I thought of the firing of a gun. Conservation momentum here. So where we start here, the rifle, the bullet in the rifle, okay, everything's at rest, right? You pull the trigger. What happens? The hammer hits the back part of the bullet. An unstable compound is in there, dynamite, okay, an explosive. When it hits the trigger, that compresses it, heats it up, just enough for it to explode. Now that's all an internal thing, okay? So when it explodes, initially the bullet's at rest, the rifle's at rest, everything's at rest, okay? But once that explosion happens, the change of momentum of the bullet is in this direction. The momentum of the rifle has to be in the opposite direction because momentum is conserved. So if the bullet takes off at this speed, the rifle has to go backwards at the same momentum. Now, big difference here, the velocity of the bullet is huge, but the mass of the bullet is very, very small, especially compared to the mass of the rifle. But that still gives it a kick, and that's a pretty significant kick. And if you've ever fired some of these sort of military-grade, lightweight weapons like they came out with in Vietnam, y'all don't remember this because it was way before your time, but the World War II, they used the old carbines or things like that, really heavy weapons. And they fired at a pretty high rate of speed, but because the gun itself was so heavy, it didn't have as much of a kick. It certainly had a kick, but not as much. Then in Vietnam, when they're having to carry the rifle over their head in the rice paddies, they wanted a lighter weight rifle. So they got it. What they didn't think about was they didn't decrease the speed of the bullet, and now the gun kicked back, and I mean, there were some separated shoulders and very bad bruising. So they had to either slow down the speed of the bullet, or else, it made for a mess because momentum has to be conserved. Now, what's the smart thing to do? If you've ever fired, especially a high-powered rifle, it will knock your shoulder. I mean, if you don't have it snug against your shoulder, you will get a huge bruise, and I have actually heard of people separating a shoulder if they hold the butt of the rifle off the shoulder. But if you hold it snug against your shoulder, what have you just done? Now this end of the equation has you and your shoulder as part of it. Your mass is now part of the system. So it's going to be much greater. It's not just the mass of the rifle, mass of you, your shoulder, your whole body, and the rifle. So now the velocity is much less. So that's why holding it tight against your shoulder will keep you from damaging your shoulder. The bullet's going to leave at the same velocity, same momentum. Yours has to be otherwise. So the total momentum of a group of interacting objects remains the same in the absence of external forces. Now, the firing of the bullet in there, that's an internal force. That doesn't affect, it affects the speed of the bullet and the speed of the rifle, but it's an internal force. Now, another example, and I know you've seen this before, if you've ever watched someone break up a pool setup, billiards, okay? When you hit that cue ball into that group of 15 balls there that are stacked in the rack there, okay? And if they're really put together well, all of them touching each other, and you give that cue ball a certain momentum, it looks like the balls are flying everywhere, and it looks like things have increased. No, the momentum of this total momentum of those balls after the collision is exactly equal to the momentum of the cue ball hitting it. The difference is some of them go forward, backward, to the side. Those that are going opposite directions are canceling each other out. The total momentum of that system is the same. The cue ball initially, the whole group of balls at the end, the total is the same. Now, some applications of conservation momentum. Collisions. And I don't know if you've hopefully never been in a car accident, but I remember, I think it may have been, no, it wasn't the first day I was on campus. It was the first day I had gone to campus early as an incoming freshman at Georgia Tech. And we were there about a week for orientation before classes began. But that weekend before classes began, my brother and he was 2 years older than me, and some friends of his and stuff were all coming back to campus. And since you weren't behind yet, you didn't have any homework yet, you had nothing to do, they decided, let's take in a movie. So I got to go to a movie. We went to see Easy Rider. Okay, y'all don't even remember that movie, but Peter Fonda and Jack Nicholson were the two stars of that incredibly good movie. Okay, we went to see it. We didn't have a vehicle. My father brought us to campus and drove home. We weren't even allowed. Well, no, I guess my brother, he was a junior that year. He could have had a vehicle, but we couldn't afford one. So anyway, he had this friend from Ohio who did have a vehicle. Nice, Z28. And he said, yeah, let's go see Easy Rider. But he wasn't sure where the theater was. Mike had a better idea. My brother, he was up front sort of navigating. I was in the back seat just in front of the right rear wheel. And so we're going along looking for the entrance to the theater, and Mike said, there it is. So Frank immediately turned, okay, across traffic and cut right in front of a car, which hit the right rear panel just behind where I was sitting, okay. When the police came out, one of the things they did, they measured skid marks. Now, in this case, it wasn't going to make a lot of difference, but guess what they were doing? they were measuring change of momentum, because the change of momentum of the system on both cars had to be equal and opposite. So that's what they do with collisions, any kind of action, reaction, interactions. Okay. And I think we are awfully close to running out of time. Let's see. The next concept here is impulse. I don't think we have time to do justice. Oh, yuck. I didn't notice example 214 is there, and I don't think we're going to have time to do it. So we'll pick up next time. That'll be Thursday, 1:15, or right thereabouts, with example 2.14. So we'll pick up there and move on from there. And I'm guessing next time we will come close. We probably will finish the chapter, and I'll probably have a test for you, probably put it out on Blackboard, covering chapter 2. All right, any questions? May have a minute or so.
Yes, sir. If we were not able to take the chapter 1 test,
Yeah.
due to all this stuff, do we need to just wait till we come back into school, or can we have it put online?
Okay, no, okay. What I'm going to have to do is go through for those people who didn't get to take it and email it to you.
Yes,
And so I'll probably be doing that possibly later this afternoon. I'm going to first be working on trying to get a lab together, and then once I either run into a dead end there or get it done, then I'll try to be emailing those people. There's also a few people who didn't get lab 0. I'm going to have to send those to them. There's a few people who I don't know who got and who didn't get lab 1. Well, I guess I do know at least one that didn't, so I'll be emailing her lab, and anyone else that lab, and then also those of you who didn't get your test, I'll have to be emailing it to you. So, yeah.
Okay, so if we have completed lab 1 also, how are we supposed to turn that in?
Okay, but you didn't turn it in, but you now completed it, right?
Yes, sir. It's
Okay.
complete. I just didn't get a chance
Do
to
you have any way of scanning it and getting it in PDF form?
should be able to.
Okay, if you can do that, then attach it to an email and send it to me.
Yes, sir.
Okay. Now I might be able to discover some way in Blackboard to do this. I don't know how to do that yet, so email would probably be easier. And
Yes,
I think
sir.
my email is listed on on the syllabus. It's listed on the locator card. It's
Yes,
all
sir.
over the place. It's cfiler@lawsonstate.edu.
All right. If I'm not able to scan it, would it be okay to just take a picture of each individual page and upload it to an email and send it to you?
Right. I think my computer will read a JPEG, which is what most pictures come out. However, my wife's cell phone, smartphone, actually will do a PDF file. So if you can do a PDF, it'll be better. But if you can't, a JPEG, I think will do. If my computer won't do it, my wife probably has a better computer that will do it. So we'll manage to get it somehow. And if I can't, I'll just go back to you and say, I can't read it or I can't print it. Can you send it to me in a PDF? So yeah, try however you can get it to me, And then once you get the test and complete it, send it back to me the same way.
Yes, sir.
Okay? Good question. Glad you asked.
Thank you.
And thanks for being here for the whole shebang. I guess Gunnar is still there too, but take care.
Yes, sir.
Okay. What's that? I can barely hear you. Oh, there you are. All right, take care. Oh, I didn't know you were there. Let me get parent marked here.
Oh, you got Diggy.
I had no idea that you were there. You didn't pop up. Have you just arrived?
No, sir. I've been here the whole time.
Okay. That's why he's almost asleep. I almost put him to sleep there, didn't I? Okay. Or any others out there? This is the only way I've got to take attendance. All right. Yeah, I got Zane. Yeah. I guess I only get to see 2 at a time.
Class starts. Okay.
All right. Take care. We'll be in touch on Thursday.
Yes, sir.
Okay, bye-bye.